Now, whenever we do statistical mechanics, we always go through thermodynamics. So, we do not need to go through thermodynamics actually. As I said, I can develop an alternative way approach to statistical mechanics as I discussed here, but standard thing of doing through thermodynamics has merit. The merit is that it allows you to go and discuss some of the things that statistical mechanics actually does. One of the main merit of statistical mechanics is that it calculates the thermodynamic properties. It calculates the entropy, it can give the free energy. That is the main merit of statistical mechanics. Now, so but other than that, Einstein wrote many things about thermodynamics. He said the only thing that will remain if everything gets, you want to send one thing, world is getting destroyed in a capsule to alien, only thing that you should send is thermodynamics, or one thing that will survive, which will be, it will never be overthrown. Okay. Now, so I will spend a little time on thermodynamics, and the reason is that again I will tell it little bit differently. I will tell it the way I looked at it. So, it is very important to realize when does thermodynamics start. Again, as I telling you again and again, if you take interest in the history of evolution, you will find it's much more interesting in whatever work that you are doing, because you will be able to relate little bit. Thermodynamics started with the Industrial Revolution. Why it started the Industrial Revolution? Because India played a very important role in this Industrial Revolution. Because of India, the 1757, that British, then the first thing they started doing, they started taking away the coal, and though England already had enough coal, but they also had steel, but those days huge thirst for the raw material, and India provided huge amount of raw material. Now, I write a blog which some of you might, there is a, Raja Rammohn Rai, who was considered the first Renaissance man in India, Raja Rammohn Rai made a fantastic calculation about the money British was taking away. Anybody knows of that amount? He figured out those days, by this raw material and everything, how much money British was taking away. Even those days, a few million pounds per week, and all in all, now the calculation is that British took away $45 trillion. It is important that suddenly enormous amount of coal, steel went to England. Same happened in A also. France also equally efficiently robbed Africa and many other things. But coming back to thermodynamics, so steam engine came, and so there was now the necessity to have an efficient engine, and that is where thermodynamics can play a role. And I am telling you again and again one very important thing, that everything is very practical. Thermodynamics was done completely because of this. Boyle was travelling in a in a ship, and he is the one who formulated the first law. Okay, so quickly go through, and again I will tell you. So as I said, statistical mechanics provides the microscopic basis in terms of atoms and molecules. So when I say microscopic basis, I say atoms and molecules, and they are interacting, their interaction potential. Boltzmann gave the meaning of entropy. There are other entropy, and I told you Einstein gave the meaning to specific heat. All these are comes from statistical mechanics. Thermodynamics limitation, all of you know, or some of you know, that it does not provide numbers, because it provides changes that all of us know, delta G equal to delta H minus T delta S. But it does not tell you how to calculate, except you had to go, when they had to calculate free energy, that is what Planck and Ernst introduced the third law, right. because to calculate other than third law you cannot calculate. Then third law combined with specific heat, temperature dependent specific heat gives you enthalpy and entropy, right. That is you have done that in A. So, that was an imperfect law, and why it was that one understands from Boltzmann, but S equal to KB, L and W, but those days people did not know of that. Okay. I will quickly go through thermodynamics and tell you something rather interesting about thermodynamics. Again, I am not going to do a full course on thermodynamics, that is beyond the scope, but many StatMag book has one very long chapter. I always thought that was not the right thing, because I am going to here study statistical mechanics. Something students should learn something new. Statistical mechanics gives me the values of thermodynamic quantities. That is an important input. That makes sense. Okay. Let us quickly go through the laws. So, you know, this is delta E, delta is missing. Okay. Q plus W, Q is the heat. So, if you are going from one state to another state, then internal energy change is delta E, and this delta is the state function, is a function of the state, does not depend on the path, but these two, heat and work, depends on the path. Now, this is a very interesting law, very interesting. Change of internal energy is sum of two path functions. So, it is a constraint. I can do Q. I am interested actually in a steam engine, or think of you guys have not seen this old, we traveled on those railway in where you have big coal, and one poor guy, he was put, there are two guys in the engine section and one putting coal into the fire and boiler and all these things, water going, and that was the force was turning the. So, all these things, heat was generating the work. But one important thing is that is not easily accessible work is to be measured and calculated. There are certain problem, but major problem is that this is one equation, but we have two unknowns. You know, I want to have a relation between Q and W, but this equation gives, other than that Q and W I can vary any way I want, but I do not know anything more than that, they have to be together, they have to be conserved. So, one equation, two unknown. This equation is not useful as you have one equation and three variables of the daily, say I can measure, but there still I have two things. So, this is very important limitation of the first law of thermodynamics, that it does not let you do anything. So, important thing is that I want to have the relation between Q and W. That then took a long time. That is the one that whole generation of scientists did that. Carnot engine and all this thing was just to get a relation between Q and W. Okay. So, well, statistical mechanics for excitation, that is not too important right now. We have to do in terms of intermolecular. Internal energy is the sum of kinetic and potential energy. So, statistical mechanics gives you certain teeth into this quantity, what is the energy. It does not tell you about Q and W, okay. Okay. Now, I will come back to that. One thing we separate out is the enthalpy, because there is a work, mechanical work, which is thermodynamics. So, we introduced the enthalpy with H equal to E plus PV. Now, come back, I will come back to intermolecular interaction, that was a digression and I do not want to do the right now. So, I continue with the second law of thermodynamics. Whole idea of Clausius, Clapeyron, Thomson, all these people were to find a relation between heat and work. And there are several statements, Clausius statement, it is, see they are trying to find a relation between heat and work. It is impossible for any cyclic machine to transfer heat from low temperature to high temperature. Kelvin's statement, it is impossible any cyclic machine to convert heat completely into work. That was the dream, to convert heat completely into work. So, all are these statements of negation. You know all of these things, you have done at least 5 times as I am telling you. So, these statements are equivalent as all of you know, but all of them are statements of what you cannot do. But then what we can do? One thing that if everybody was interested, how to find the maximum amount of work out of heat. I have delta E conserved. Now I want a relation between Q and W which satisfies that particular way of doing which will maximize. Those days in industrial revolution there was a tremendous on the efficiency, and efficiency of Carnot engine and all these things was it was very practical. They wanted to increase the efficiency of a steam engine, and steam engine was there everywhere, in train, was pulled by in ships, everywhere. Okay. Then one thing they realized that, well, they cannot find a relation between heat and work because both are path functions, but if they do it so slowly from one state to other state, then they will be able to do something. That means if they you move so slowly, then I am, what is the reversible path? I can go from one state to other state, and along the path the Carnot showed that I can introduce the entropy. So, this is the thing all of you know, that it is T is, I do not know why, okay, the capital T, and so this is the Clausius inequality. Important thing here is the equality, that Q is the reversible and T is the temperature, and this equality holds for reversible process, and the equality is the one that then allows us to derive all the free energy. Now, why free energy is so important? Can anybody tell me why free energy is so important? Why so much work? Carnot engine, 2-3 chapters of thermodynamics, at the end of the day we get a free energy. Why so much attempt was made to get the free energy? Absolutely, it is the energy free to work. So, the part that we cannot do anything is entropy. So, now you understand the whole second law. So much work by so many smart people was done to derive an equation of this kind under different conditions. Okay. So, that was the, so the two new things, somewhat new things that I have told you. The first law give you a relation between work and heat, but it is an equation, one equation, two unknown, and so I need a between Q and W, and then there is a huge amount of work went into. All the smart people in Europe tried to get the relation. They cannot do it if it is irreversible because it is arbitrary, but if you go infinitely slowly by going from one equilibrium state to another equilibrium state to another equilibrium state, piece together, then you get what is Clausius equality part of the inequality. Inequality part is not too useful other than sometime in universal thermodynamics, but not in equilibrium thermodynamics. Equilibrium thermodynamics, it is the equality part that is important, and that ultimately leads you to these things, and this is the of the energy change, this is the one that is getting lost. So, this is the one that is free to do work. Now, I have an upper bound of the efficiency because I know how much entropy I can, how much work I can extract from an internal energy. So, this is just one free energy surface that I will talk a little later. Let me go back. One important thing of statistical mechanics is that what started with van der Waals and Boltzmann, not that much Maxwell, but Boltzmann, was that the two particles interact. So, intermolecular interaction plays an essential role in our understanding, because why? Both in physics and chemistry, but particularly more in chemistry, that we want to think of two molecules that are interacting. So, all the properties, whether it is specific heat, whether it is density or any dielectric constant or conductivity, all are determined by the intermolecular interaction. That means two molecules are coming together, and when there is one molecule, I put it at the center of my coordinate system, then I bring one more molecule. And what is the interaction? When they overlap here, then there is a large repulsion. So, basic part then, and then in A there is attraction because of electronic fluctuations wave function that we are not going to go into. So, this is the separation between two particles, and this is what is called intermolecular interaction. So, then this whole idea of statistical mechanics is that if I give you this intermolecular interaction, starting giving you this intermolecular interaction, can you give us everything else? Can you give us the specific heat? Can you give us the phase transitions? Can you tell us why water freezes into ice at 0 degree centigrade and goes into vapor at 100 degree centigrade? So, all these things, so statistical mechanics claims, that was the dream of Boltzmann, that starting with a bare potential, there are three things given here. This is the one that I drew here, it is called Lennard-Jones. This is a hard sphere of the billiard model, that is no interaction till they touch, and when they touch they go to infinity. Another one sometime used is called square well, that means there is an attraction, then 0, and then harsh repulsive potential. Interestingly, such a simple potential is the simplest possible potential that describes liquid to crystal transition fairly accurately, and that captures the essence of freezing, however surprising that may appear to you. This is the one, and these two describe both gas to liquid, liquid to crystal, many other things. For example, if I want to do water, then water will be somewhat more complex potential, but not to there are no orientation dependent potential, but it is like that. So, now think of the following, that we have done little bit of thermodynamics. First law, Boyle, that is essentially Boyle formulated, second law by many people, given to entropy and free energy. We have our agenda fixed, and well, there is not one agenda, there are many agenda. One of them is that how can I calculate the properties of a matter, and to start with the calculation of properties of matter, if I want to calculate entropy from a first principle, I want to calculate the specific heat, I want to calculate say conductivity or isothermal compressibility or phase transition, what is the latent heat of freezing, what is the latent heat of evaporation. I want to calculate, I know what is the binary property of water and ethanol, why there is a eutectic point at 95% of water ethanol mixture. So, why when I add little DMSO, why does lysozymes, this cell oil breaking lysozyme CO bond get accelerated by a factor of 3, why protein folds to its structure native state. So, statistical mechanics has this agenda, the grand agenda, that you give me this interaction potential and I give you answers to all the questions. That is the basic idea of statistical mechanics, and it can be broadly divided into two parts, equilibrium and non-equilibrium. What we are going to say in the beginning is equilibrium, because if you do not do equilibrium stat mech, you will not be able to do non-equilibrium stat mech. You need to know how particles, just like Gibbs did, gave away the path of Boltzmann, because he realized equilibrium is much simpler, or rather there is a simpler way to do the equilibrium statistical mechanics. Okay. So, that vision and that brilliant understanding of Willard Gibbs, but by that time of Willard Gibbs and by the time of Boltzmann and of course Einstein, they already had this agenda. They knew that you give me an interaction potential. Then the idea was that how simple can be. It turned out, as I told, gas to liquid cannot be explained by that, but liquid to crystal can be explained by these very simple potential. They can explain both gas to liquid and liquid to crystal. This, how do you get the interaction potential? I can give you a flow chart, is that you start from quantum mechanics and quantum mechanics gives you the interaction potential. Once you get the interaction potential, then you get, from the interaction potential you get all the properties. I am not really lying to you and I am not bragging, I am not saying, but that is really the agenda and promise of statistical mechanics which has been largely fulfilled. This realization of the promises, but it took more than 100 years, particularly advances of computer simulation, because many of the equations which Boltzmann could not do or Gibbs could not do, we can do it by computer simulation. Now of course, you always have to do analytical work because the analytical models tells you how to go, then you do more complex things. So again, to formulate the starting from Boltzmann, who introduced intermolecular potential, Boltzmann considered this potential. In his case it was a hard disk or hard spheres, billiard ball model. Only 2 of them he considered, he could not consider 3. As I said, even now 3 body problem is unsolved in analytically. Then came of course much later in 1930s or these things were done. Now I think I will stop here today. The interaction potential business and the subsequently we will start from the statistical mechanics. Just in quantum mechanics we start with Schrodinger equation. In statistical mechanics we need certain postulates. So these postulates of statistical mechanics, as Einstein repeatedly says, the simplicity of a theory is based on how few assumptions you can make and then how far you can go. The statistical mechanics, whose goal is starting with an intermolecular potential to go to thermodynamic properties or realistic properties, that builds only on 2 postulates and 1 hypothesis. And so in the next class, what I will do, so what I have done today, give the history and did the thermodynamics, and in the next class I will start with the postulates of statistical mechanics, and then from postulates, these postulates, one of the postulate was done by Boltzmann, which is the time average. Second postulate was done by Willard Gibbs, which is the ensemble, and these 2 combined with the help of a hypothesis, and that goes into the development of, leads to the development. So the way it happens is that you have the postulates and the hypothesis that allows you to go definition of certain quantities called partition functions, which immediately gives you thermodynamic properties. So after that we will do certain simple models, just like in quantum mechanics, like we do you do particle in a box, we will do ideal gas, we will do harmonic oscillator, just like in quantum mechanics we do harmonic oscillator, here we will also do harmonic oscillator. That you will see will goes to Sackur-Tetrode equation and many equations which are still used today. Then you do rigid rotator, same you do quantum mechanics, we do in statistical mechanics rigid rotator. So you will find that the certain sense, the step by step thing of statistical mechanics parallels quantum mechanics, and the step by step thing was done. Just Schrodinger did the quantum mechanics. It was the Wheeler Gibbs who did all these things for statistical mechanics. And in the process you will see again we derive ideal gas law, we will be deriving something like van der Waals, but now with an intermolecular potential. Van der Waals had an imperfect and incomplete intermolecular potential, but we will now be able to do in a more complete way. So now I think I will stop here today, but I will take some questions. No, this is one very pure equilibrium means you do not go anywhere. Pure equilibrium means you stay there. So here you are making infinitesimally small changes. You are making so small change that you can talk like the concept of virtual work. You do a very small amount of thing and you say that I can apply equilibrium principle. So you are not at equilibrium, you are inducing a change, but change is done such a small step that you can say okay I am going from A1 to A2, but I can now talk of thermodynamics, I can talk of equilibrium principles inducing the small change. So it is like that, you going from one to next and you do by infinitesimal change. Now the next step you are doing from say step 1 to 2, then step 2 to 3, all of them pieced together give you a, it is not equilibrium but it is a reversible. Okay. So if you do a reversible change, then I think I do not have any control anymore. I go from in a big jump or finite jump from one state to another state. Then all I have is that relation, go back to your first law, and you have an inequality. But inequality does not help you because it is ill defined. So you strive to get the equality, and it was derived in classical mechanics. We have this virtual work, we do very small amount of work, but then we use thermodynamic principle to get that. So it is exactly that somewhat funny concept that you are doing infinitesimally slowly to that unique path which is the reversible path. It is confusing all the way, and except that it is what Carnot showed by this reversible path, that you can show that dq by t, dq reversible by t is the path function, is independent of path. That was the, there is a beautiful proof, and the only place such a good proof is given is in Castellan, where he showed that you can piece together these and get a state function. So whole idea is that dq reversible by t is proving that is a state function for a reversible path. That is the Carnot engine, and then Carnot engine, then I have to do the thermodynamics which I do not want to do, but when Carnot engine was that, next proof came that dq reversible by t over a cyclic path.